parameter becomes 0. So we will substitute a is equal to 83 and b is equal to 19. When we substitute a is equal to 83 and b is equal to 19, then we will get GCD of b comma, which is GCD of 19 comma 83 mod 19, right? So when we simplify this, we get GCD of 19 comma 83 mod 19. We will get the remainder as 7. So we get GCD of 19 comma 7. Are we going to stop this? No, the second parameter is not 0. That is b is not 0. So we are going to recursively apply this formula till this part becomes 0. So here a is equal to 9 and b is equal to 7. So we are going to compute GCD of 19 comma 7, which gives GCD of b comma a mod b. So b means 7, 19 mod 7. So when we simplify this, we get GCD of 7 comma 5. So second parameter is not 0. We are going to apply this algorithm again. So GCD of 7 comma 5 will give GCD of 5 comma 7 mod 5. So when we simplify this, we get GCD of 5 comma 2. Still the second parameter is not 0. So again we are running this algorithm. So GCD of 5 comma 2 will give GCD of 2 comma 5 mod 2. Why? Because this is b, this is a mod b. Because a is 5, b is 2. So GCD of b comma a mod b. This formula, right? Now when we simplify this, we get GCD of 2 comma 1. Still the second parameter is not 0. So I am running the algorithm again. So GCD of 2 comma 1, we get GCD of 1 comma 2 mod 1. So 1 comma 2 mod 1 will give 1 comma 0. So 2 mod 1 will give the remainder 0. Now the second parameter is 0. Whatever is there in the first parameter. In other words, when b is 0, a is the GCD. What is the value of a now? It's 1. So we get the answer as 1. It means these numbers 83 and 19 are relatively prime. Are you wondering that I'm using the term relatively prime for the first time in this lecture series here? No worries. In the next lecture, we are going to see relatively prime numbers. There we need the concept of finding the GCD of two numbers in order to check whether the two numbers given are relatively prime to each other or not. Before we sign out, let's see the homework question. The question is, find the GCD of 529, 123. You can either follow method 1 or method 2. After solving this, I request you to post your answers in the comment section. And that's it, guys. I hope now you understood the Euclid's algorithm to find the GCD of two numbers in a detailed manner. I hope you guys enjoyed this presentation and thank you for watching. Hello everyone, welcome back. In this presentation, we will focus on relatively prime numbers. Relatively prime numbers are also called as co-prime numbers. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to understand the need for finding GCD. And outcome number 2, we will understand relatively prime numbers, which is also called as co-prime numbers. Before stepping into the topic of the day, relatively prime numbers, we will just recap what is GCD. The GCD stands for the greatest common divisor. GCD is also referred to as HCF, which is highest common factor. Divisor and factor refers to the same concept. Already we have seen about finding the GCD of two numbers in the previous lectures. With the knowledge of GCD, we are stepping into the next lecture, the relatively prime numbers. Let's see what is relatively prime numbers. Before seeing the details of relatively prime numbers, let's see the definition first. Two numbers are said to be relatively prime if they have no prime factors in common and their only common factor is 1. When we have two numbers, then we will call these two numbers are relatively prime to each other when they don't have any common factor except 1. So that is what the definition says. Let's see it elaborately. Let's say we are taking a and b are two numbers. When a and b are said to be relatively prime numbers, a and b are said to be relatively prime numbers when they don't have any common factor except 1. In other words, if the GCD of a and b is 1, then 1 is the only divisor that can divide both a and b, right? So if the GCD of a and b is 1, then a and b are said to be relatively prime numbers or co-prime to each other. So I already told you relatively prime numbers are also referred as co-prime numbers. So before we see the examples, just have this in mind. Two numbers are said to be relatively prime to each other or co-prime to each other if they don't have any common factor except 1. In other words, if the GCD of those two numbers is 1 or the HCF of those two numbers is 1, then these two numbers are said to be relatively prime numbers. Let's see some examples, then you will understand things clearly. Let's see example number 1 first. Are 4 and 13 relatively prime? Now we are going to find whether numbers 4 and 13 are relatively prime to each other or co-prime to each other or not. Let's solve this manually. So we know the numbers that are given are 4 and 13. When we will say 4 and 13 are relatively prime to each other, when the GCD of these two numbers is 1, right? Let's take both the numbers. We are going to find the GCD for 4 and 13. What all the divisors of number 4? The divisors of number 4 are 1, 2 and 4. What all the divisors for the number 13? Please note here 13 is a prime number, so obviously the divisors will be 1 and 13 because prime numbers will have only two factors. One is number 1 and the other one is the number itself, right? Now in these two set of numbers, what's the common divisor? We have 1 to 4 here, we have 1 13 here. So the common divisor here is 1 and obviously this is the greatest common divisor. So it's clear that the GCD of 4 and 13 is 1. So when the GCD of these two numbers is 1, obviously 4 and 13 are relatively prime to each other. So the answer for question number 1 is yes, 4 and 13 are relatively prime numbers. If you note here, you have a prime number here, but this number is not a prime number. Don't get confused with prime number concept with relatively prime numbers. We have already seen about prime numbers elaborately, so it need not be the case that two prime numbers only should be relatively prime to each other. Don't worry about this now. Anyway, before we sign out, we are going to see some scenarios with two different numbers, how they are relatively prime to each other. We are done with question number 1. Let's move on to question number 2. In this question, we are going to find are 15 and 21 relatively prime. We know we are going to follow the same manual approach, so we are going to find the divisors, followed by the common divisors and the greatest common divisor. Let's solve this now. The first number is 15 and the second number is 21. We are going to find the factors for 15. The factors for 15 are 1, 3, 5 and 15. And what about the factors for 21? The factors are 1, 3, 7 and 21. I already told you factors are also referred as divisors. So we have found out the factors for 15 and 21. Now we will find out the common factor or common divisors. Here we have 1 and 3, here also we have 1 and 3. And no other numbers are matching. So the common factors or common divisors are 1 and 3. Out of 1 and 3, what is the greatest common divisor or highest common factor? Which is 3 here, right? So 3 is the biggest number. So the GCD of 15 and 21 is 3. So the answer to this question, are 15 and 21 are relatively prime? No, 15 and 21 are not relatively prime numbers. Now I'm going to show you an example which we have seen in the previous presentation, where in the last presentation we have seen this example 2 to find the GCD of 83 and 19. I hope you can remember this. If not, I request you to watch my previous lecture and we confirm the GCD of 83 and 19 is 1. So when the GCD of two different numbers is 1, then it means these two numbers are relatively prime. If you are given with a question to find the relatively prime numbers, I recommend you to apply the Euclid's algorithm and you find the GCD. If you get a number which is not 1, then obviously it means these two numbers are not relatively prime. If you get the GCD as 1, then it means these two numbers are relatively prime. Before we sign out, let's see various scenarios. So I'm going to have 5 columns here. Two numbers A and B we are going to take, and we are going to find whether A and B are relatively prime to each other with various scenarios. In order to verify whether they are relatively prime numbers, we need the GCD, right? So I'm computing GCD value. Now, with the result of this GCD calculation, I'm going to confirm whether the numbers are relatively prime or co-prime to each other. And I have a remarks column. Let me explain that now. First, we are going to take two different numbers, say 11 and 17. Here, if you observe, 11 is a prime number and 17 is a prime number, right? So when we have A and B are prime numbers, obviously they are different prime numbers, isn't it? So for different prime numbers, the GCD value will be obviously 1, isn't it? When the GCD is 1, obviously they are relatively prime to each other. So in the first scenario, we have confirmed A and B are prime, and A and B are different prime numbers, and hence they are relatively prime to each other. Is there any rule that A and B should be always prime? No. Just see the second scenario. In the second scenario, we have A as 11, which is a prime number. We have B, which is 21, which is a composite number. So 21 is a composite number. Why? Because it has factors other than 1 and 21. It has 3 and 7 also as factors, right? So 21 is not a prime number. But still, when we compute the GCD of 11 and 21, we get 1 only as the GCD, because there are no common factors that can divide both 11 and 21 except 1. So in the second scenario, where one is a prime number and the other one is a composite number, which is this. So A is a prime number and B is a composite number, but still they are relatively prime to each other. Can we conclude like this? If any one of the numbers is a prime number, then it should be relatively prime. No, we cannot conclude like this. I'm going to show a third scenario where the numbers A and B are not prime, they are composite. Can you see here? I'm taking A here. A is 12, which is definitely not a prime number, and 77, which is also not a prime number, because 77 has factors like 1, 7, 11, and 77. So it's clear that A and B are not prime numbers, they are composite numbers, but still the GCD is 1, because 1 is the only number that can divide both 12 and 77. So in this scenario also, these two numbers are relatively prime to each other. I hope this slide had demystified you that we should not take the decision of confirming whether they are relatively prime or not relatively prime by just looking at the numbers. We need to compute the GCD, and then we should confirm whether they are relatively prime or not relatively prime. So I hope now you know the need for computing the GCD to ensure whether they are relatively prime or not. So I always recommend you to apply Euclid's algorithm to compute the GCD and then take a decision based on the result of the GCD. I hope relatively prime numbers concept is clear to you. And that's it, guys. Before we sign out, let's see the homework question. The question is, find the GCD of 790, 121 using Euclid's algorithm. After finding the GCD, you are required to determine whether they are relatively prime to each other or not. I request you to solve this homework problem and post your answers in the comment section. I hope now you understood the need for finding the GCD, and we also have understood the relatively prime numbers or co-prime numbers. I hope the session is informative, and thank you for watching. In the last presentation, we have seen about relatively prime numbers, which are also called as co-prime numbers. In this presentation, we will see about the Euler's torsion function, which is also called as phi function. Let's see the outcomes first. Upon the completion of this session, the learner will be able to, outcome number 1, we will understand the Euler's torsion function phi of n, and outcome number 2, we will understand how to find this Euler's torsion function phi of n. Let's dive into the topic of the day, the Euler's torsion function. Euler's torsion function is actually denoted as phi of n. What is this phi of n? This phi of n is the number of positive integers that are lesser than n that are relatively prime to n. I know it will be difficult for you to understand now, but But this concept will be clear when we see some examples. Let's dive into the first example. Example number 1. Here we are going to find phi of 5. So here n is equal to 5. Let's solve this and understand what is this Euler's torsion function phi of n. We know the n value which is given here is 5, right? So as per the definition, how many numbers that are less than n are relatively prime to n is phi of n, isn't it? So here n is equal to 5. So the numbers that are lesser than n are 1, 2, 3 and 4, because here n is 5. So numbers less than 5 are 1, 2, 3 and 4. So out of these numbers, how many numbers that are relatively prime to n? So we need to check, is 1 and 5 are relatively prime, 2 and 5 are relatively prime, 3 and 5 are relatively prime, and 4 and 5 are relatively prime. So we need to check how many numbers that are less than n, that is these numbers, that are relatively prime to n. So that's what we are going to find. So as per the definition, we are taking only the number of positive integers that are lesser than n, that are relatively prime to n. For example, if we are going to compute phi of 3, then we are going to focus on numbers that are less than 3, which are 1 and 2 only. We are ignoring 0, -1, -2, all negative numbers. They are also lesser than n, isn't it? Because the definition says we are going to focus on number of positive integers less than n are relatively prime to n. So it means obviously we are ignoring 0 and minus numbers or negative numbers. In the last presentation, we understood that when two numbers are said to be relatively prime. For that, I asked you to compute the GCD. For computing the GCD, I recommended you to use the Euclidean algorithm, right? Anyway, we are going to find the GCD. So I'm going to compute the GCD, and I'm going to confirm whether it is relatively prime or not. So I'm going to compute GCD of 1, 5, 2, 5, 3, 5, and 4, 5. So let's check it out. So GCD of 1, 5, GCD of 2, 5, GCD of 3, 5, and GCD of 4, 5. So we can see that GCD of 1, 5 is 1, 2, 5 is 1, 3, 5 is also 1, and 4, 5 is also 1. If you want to know how to compute the GCD using Euclid's algorithm, I request you to watch my previous lectures where I have computed GCD using two methods. methods. You can pick and choose any one of the methods, whichever is comfortable to you. Whenever the GCD of two numbers is 1, then that number is said to be a relatively prime number. In this case, 1 and 5 are relatively prime, 2 and 5 are also relatively prime, 3 and 5 are also relatively prime, and 4 and 5 also are relatively prime numbers. As per the definition, how many numbers that are less than n are relatively prime to n? 1, 2, 3, 4. So there are 4 numbers that are lesser than n that are relatively prime to n. So there are 4 numbers that are less than n are relatively prime to n. So the answer is phi of 5 is equal to 4. It means there are 4 numbers. What are these numbers? 1, 2, 3, and 4. All these 4 numbers are lesser than n, right? Yes, they are less than 5 and they are relatively prime to 5. So the answer for this question is phi of 5 is equal to 4. Let's see another example where you will get more idea about this. In this example, we are going to compute phi of 11. We know the given data n is equal to 11. So we are going to find how many numbers that are less than 11 are relatively prime to 11. So we know the numbers that are less than 11 are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we are going to find how many numbers in these 10 numbers that are relatively prime to 11. So we are going to obviously compute the GCD, right? So we are going to compute the GCD of 1, 11, 2, 11 up to 10, 11, right? So let's see that now. So we are going to compute the GCD of 1, 11, 2, 11, 3, 11, 4, 11, 5, 11, 6, 11, 7, 11, 8, 9, and 10, 11, right? Are 1 and 11 are relatively prime numbers? Yes. What about 2 and 11? Yes. When the GCD is 1, then they are relatively prime numbers. So in this example, we can see 3, 4, 5, 6, 7, 8, 9, and 10 are relatively prime numbers to 11 because the GCD is 1, isn't it? So in all the cases, the GCD is 1. So there are how many numbers that are relatively prime to 11? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 numbers that are relatively prime to 11. So it's clear that the answer for this question is phi of 11 is equal to 10. Now let's see the last example. Find phi of 8. So we are going to adopt the same methodology what we had followed in both the examples previously. So the solution goes like this. Here n is equal to 8. So we are going to list the numbers that are less than n, which is from 1 to 7. So we are going to compute the GCD, right? So GCD of 1, 8, 2, 8 up to 7, 8. Now in this case, if you see here, GCD of 1, 8, 1 is the answer, right? Whereas here GCD of 2, 8, 2 is the answer. GCD of 3, 8, 1 is the answer. GCD of 4, 8, we have 4 as the answer. 8 we get relatively prime to 8. 3 is relatively prime to 8. Now numbers that are relatively prime to 8. So phi of 8 is equal to 4. I am asking you to GCD of 999, C in the next lecture in an easier manner. So keep the fingers crossed. In the next lecture, I will explain you how to compute the Euler-Stoichern function or phi function for bigger numbers using formulas. And that's it, guys. I hope now you understood the Euler-Stoichern function phi of n, and also we understood how to find phi of n. I hope you guys enjoyed this presentation, and thank you for watching. In the last presentation, we understood the basics of Euler-Stoichern function. Euler-Stoichern function is also called as phi function, and in the last presentation, we understood how to compute the phi of n. In this presentation, we are going to have some solved examples in Euler-Stoichern function. Let's see the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the Euler-Stoichern function, which is also referred as phi function, and outcome number 2, we are going to understand how to find phi of n using formulas. In the last presentation, we did phi of n calculation manually, but this manual approach will not work when the number is big. In other words, this manual approach will not work if n n is a bigger number. So we need to find some shortcuts in order to find out the value of phi of n. And that's what the main objective of today's presentation. Let's see the formulas now. We are obviously going to compute phi of n, and here I have mentioned 3 criteria for n. This n is a prime number, this n is a product of 2 prime numbers, or this n is a composite number but not product of 2 prime numbers. Let's understand one by one. If we are going to compute phi of n, and if this n is a prime number, and you need not Not manually do the calculations. Simply you can calculate phi of n is equal to n minus 1. For example, if the number n is 7, 7 is obviously a prime number. So if you are going to calculate phi of 7, then the answer is phi of 7 minus 1 is 6. So there are 6 positive integers that are less than 7 are relatively prime to 7. That is what the Euler's quotient function is all about. So this is what the first criteria when n is a prime. That is this n. If this n is not a prime number, but it is a product of two different prime numbers, say p and q. For example, 21. So 21 can be a product of two different prime numbers, 3 and 7, right? So in such case, you need not manually calculate phi of 21. Rather, you can apply this formula, phi of n is equal to p minus 1 into q minus 1. In the example, we have taken 3 into 7, right? Because we have taken n as 21. So 21 can be 3 into 7. So the answer for phi of n can be, if p is 3, so which is 3 minus 1 into 7 minus 1. In other words, 2 into 6, 12, right? So phi of 21 is equal to 12. No worries. Anyway, when you see some examples, you will understand things clearly. Let's see the third scenario. The third scenario is where we have n, where this n is a product of two different numbers, but these two are not prime numbers. They are composite numbers. In other words, either a is a composite number, or b is a composite number, or both a and b are composite numbers. In the previous case, we had a composite number n, but still that composite number is a product of two different prime numbers. There are situations where this n is a composite number like the previous case, but this n is not a product of two different prime numbers. It is a product of two different composite numbers, or one composite number and one prime number, or both are composite numbers. In such case, we need to have some formulas, right? So the formula is phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 by p3, and you continue this as long as you get the distinct primes. Here p1, p2 are prime numbers. I know it will be difficult for you to understand this part. Anyway, don't worry about this now. When we see some examples, you can easily understand. While waiting, let's dive into example number 1. In the first example, the question is, find phi of 5. We have already solved this in the previous lecture, but in the previous lecture we did it manually, isn't it? But see here how simply I'm calculating. Here n is equal to 5 because that is what is given in the question. Is n a prime number? Yes, 5 is equal to 5 numbers that are less than. I think the exact, n is given as 31, so obviously 31 is a prime number. So for this question is, well, if n value is a prime number, we can easily compute phi of n as n minus 1. But what if n is not a prime number? So let's see that kind of examples also. Let's step into example number 3. In example number 3, we are going to compute phi of 35. So let's solve this now. Now we can clearly say that 35 can be factored into 5, and the formula is 5 to 24 precise. That our should have followed this approach, right? So we are starting from GCD 1, 35, 2, 35, 3, 35 up to GCD 34, 35. And obviously we are going to compute whether they are relatively prime. If the remainder is 1, then obviously they are relatively prime, isn't it? So if you compute here, there are certain numbers that are relatively prime to each other. Say 4 and 35 are in 5. So if you did this here, it's so simple because 35 is a product of two different prime to compute 5, right? Very different. If you're going to compute 5, I told you, things are matching, right? And phi of 1000, it is a time consuming process if you manually do it like GCD of 1, 1000, GCD of 2, 1000 up to GCD of 999, 1000. At the same time, if this number 1000 can be a product of two different prime numbers exactly, then we can go for the formula phi of n is equal to p minus 1 into q minus 1. But we can't expect all the numbers to be falling with criteria 1 or criteria 2. There are chances for criteria 3 as well, isn't it? And that's why we have landed up with example number 4. If you factor this 1000, you will get 2 power 3 into 5 power 3. See, if you factor this, you may get 100 into 10 also, right? 100 into 10, again you factor. When you factor to the core, as I already mentioned when I explained you about prime numbers, ultimately the base numbers will be prime numbers, right? So any number if you factor, ultimately the base number will be prime numbers. 55 into 8 is or 50 into 20, but ultimately when you divide to the core, you will get prime factors. So we are factoring this like this. So how many distinct prime factors we have? One is 2 and the other one is 5. So we are getting distinct prime factors are 2 and 5. So here we have two different prime numbers. So we are taking the formula like this. Phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2. In case if you are having other prime numbers, extend this as long as you have the number of prime numbers. Say if you have two more prime numbers here, then you make it like 1 minus 1 by p3. Additionally, you just add it and 1 minus 1 by p4. Since we have only two distinct prime numbers, I am restricting this formula up to p2. Now we know what is p1, right? Which is 2. We know what is p2, which is 5. They are distinct prime numbers. So I am just substituting this, and after evaluation, I'll be getting phi of 1000 as 400. So the answer for this question is 400. See how easily I solve this. It doesn't mean that we cannot manually solve this, but think of if you go and do it manually. So obviously time consuming, but we got that there are 400 positive integers that are less than 1000 are relatively prime to 1000. How easily we obtain this? Let's see one more example. Example number 5, which is finding phi of 7000. So here n is given as 7,000, right? This 7,000 can be written as 2 power 3 into 5 power 3 into 7 power 1. So obviously we have distinct prime numbers as 2, 5 and 7. You need to add one more prime number here in the formula, which is phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 by p3. We have only 3 distinct prime numbers. Now let's solve this now. So when you apply p1 as 2, p2 as 5 and p3 as 7, after simplification we get the final result as 2,400. So the final answer for this question is 2,400. It means there are 2,400 positive integers that are less than 7,000 that are relatively prime to 7,000. And that's it, guys. Before we step out, let's see the homework question. I have given 2 homework questions. You are required to find phi of 369 and find phi of 372. After solving this, I request you to post your answers in the comment section. I hope you guys understood what is Euler's quotient function phi of n, and we also have seen various formulas for doing this. For criteria 3, we have other formulas as well, but in this lecture I have presented one of the formulas. I think this formula will be easy for you. I hope you guys enjoyed this presentation, and thank you for watching. In this presentation, we will focus on Fermat's little theorem. Let's dive into the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will know the Fermat's little theorem, and outcome number 2, we will understand the working of Fermat's theorem with examples. Let's dive into the theorem first. This Fermat's little theorem states that if p is a prime number and a is a positive integer not divisible by p, then a power p minus 1 is congruent to 1 mod p. So if you note here, this Fermat's little theorem states that when you take a prime number p and a positive integer a, any positive integer a, but the only condition is this a is not divisible by p. So that is what the Fermat's little theorem initial condition is. If these two conditions are set, like p is a prime number and a is any positive integer not divisible by p, then a power p minus 1 is congruent to 1 mod p. This theorem will be really helpful in solving a lot of cryptographic problems. We have witnessed a lot of positive comments about Neso Academy that Neso Academy presents the content in a structured and an organized manner. And here is one more proof for that. Can you see here, already we have seen about congruences in the previous lectures. We have already dealt about the modular exponentiation, that too with these kind of powers, right? So a power p minus 1 mod p. Also we have seen about the prime numbers in the previous lectures. So solving problems using Fermat's little theorem becomes an easy task for us because we have acquired all the basics that are required to solve these kind of problems. While waiting, let's dive into example number 1. Does Fermat's theorem hold true for p is equal to 5 and a is equal to 2? We are required to check whether the Fermat's theorem holds true for these values. Let's solve this now. So what are the given information? P is equal to 5 and a is equal to 2, right? So we have the prime number as 5 and a is equal to 2. Let's verify the initial conditions are met. Is p a prime number? Yes, this 5 is a prime number. Is a positive integer? And a is not divisible by p. So the initial conditions are met. So we can blindly say that Fermat's theorem holds true for p is equal to 5 and a is equal to 2. Anyway, let's prove this. As per the Fermat's theorem, we know a power p minus 1 is congruent to 1 mod p. Let's just substitute those values. So we get 2 power 5 minus 1 is congruent to 1 mod 5. So 2 power 5 minus 1 is actually 2 power 4. So 2 power 4 is congruent to 1 mod 5. You can use modular exponentiation, or simply you can use this value. 2 power 4 is 16. So we get 16 is congruent to 1 mod 5. We know how to solve this, right? So this number 16, when it is divided by 5, are we getting 1 as the remainder? Yes, 16 when it is divided by 5, 5 3 times 15, and the remainder is obviously 1. So we can conclude that Fermat's theorem holds true for p is equal to 5 and a is equal to 2. This is the answer for this question. I hope example number 1 is clear to you. Let's see example number 2. In this example, we are going to prove Fermat's theorem holds true for p is equal to 13 and a is equal to 11. So let's solve this now. We know the given data are prime number 13 and the positive integer a is 11, and this 11 is not divisible by p. So let's prove this anyway. So we know Fermat's theorem states that a power p minus 1 is congruent to 1 mod p, where a is any positive integer. So let's substitute the values what is given in the question. So we get 11 power 13 minus 1 is congruent to 1 mod 13. So we'll simplify this. 11 power 12 is congruent to 1 mod 13. So we are going to use modular exponentiation to solve this. 11 power 12 mod 13. But when you refer my previous lectures titled modular exponentiation, I have given a lot of shortcuts for solving these kind of problems. So here you just see it is 11, it is 13, right? We can reduce this value. So 11 is 2 shortage from 13. So we can use it as minus 2 whole power 12 is congruent to 1 mod 13. Now we can easily simplify this. You can simplify this using any method, but see how I am doing here. I'm just breaking this 12 into 4 into 3, right? So minus 2 power 4 into 3 is congruent to 1 mod 13. We get 3. How we are getting 3 here? Minus 2 to the power 4 is what? 16, right? 16 to the power 3, right? So 16 when it is divided by 13, what we will get? 16 divided by 13, we get 3 as the remainder. So we get 3 to the power 3. This power 3 remains the same. So 3 to the power 3 is what? 27. So 27 when it is divided by 13, 13 2 times 26. So Fermat's theorem holds true for p is equal to 13 and a is equal to 11. See, you can solve this in any method, but I request you to apply the easiest way of solving this problem without using calculators. So I think example number 2 is also clear to you. So we are clear that Fermat's theorem holds true for p is equal to 13 and a is equal to 11. Let's see the last example for the day, example number 3. The question is, prove Fermat's theorem does not hold for p is equal to 6 and a is equal to 2. If you see here, this p is not a prime number. So from this, we can easily conclude that Fermat's theorem will not hold true because p is not a prime number, because 6 is not a prime number. If the number what is given for p itself is not a prime number, we can easily say that Fermat's theorem will not hold true for these values. Anyway, let's solve it. We know as per the Fermat's theorem, a power p minus 1 is congruent to 1 mod p. We will apply the values. 2 power 6 minus 1 is congruent to 1 mod 6, and 2 power 5 is congruent to 1 mod 6. We will directly use this value 2 power 5, it is 32, right? So 32 is congruent to 1 mod 6. 32, when it is divided by 6, what we will get? The remainder is 2. So this is an invalid congruence. So obviously the answer for this question is Fermat's theorem does not hold true for p is equal to 6 and a is equal to 2. Before we complete this lecture, let's see the homework question. The question is, does Fermat's theorem hold true for the prime number 11 with the integer 5? I request you to solve this and post your answers in the comment section. I hope now you understood the Fermat's little theorem, and we also have understood the working of Fermat's theorem with examples. Please note here, in this subject, we are going to use the Fermat's theorem as an application. So I'm not going to prove Fermat's theorem. Rather, we are going to use the Fermat's theorem to solve our problems in cryptography. And that's it, guys. I hope the session is informative, and thank you for watching. In the last presentation, we have seen Fermat's theorem. In this presentation, we will see Euler's theorem. Let's dive into the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will know the Euler's theorem, and outcome number 2, we will understand the working of Euler's theorem with examples. By waiting, let's see what Euler's theorem states. The theorem states that for every positive integer a and n, which are said to be relatively prime, then a power phi of n is congruent to 1 mod n. If you compare this with the previous theorem, that is the Fermat's theorem, you can see here, in the previous theorem, this a is any positive integer, and we had p as a prime number. But here, there is no any such restriction like prime number. Here we can take any number n, but we are taking a to be a positive integer. But we have one more condition, where a and n are relatively prime to each other. When these conditions are met, then a power phi of n is congruent to 1 mod n. We have already seen what is phi of n in the previous lectures. What is this? It's the Euler's totient function. So remember, we need Euler's totient function for proving this Euler's theorem. Let's dive into example number 1. The question is, prove Euler's theorem holds true for a is equal to 3 and n is equal to theorem. Let's dive into example number 1. The question is, prove Euler's theorem holds true for a is equal to 3 and n is equal to 10. Here a is any positive integer and n is any number, and what's the initial condition that should be met in order to prove this Euler's theorem? Condition is this a and n should be relatively prime to each other. What do you mean by this? It means the GCD of 3, 10 is 1. Is 1 is the only number that can divide both 3 and 10? Yes, 1 is the only biggest number that can divide both 3 and 10. So obviously, Euler's theorem will hold true for these values. Anyway, let's prove that now. We know the given data are a is equal to 3 and n is equal to 10, and Euler's theorem states that a power phi of n is congruent to 1 mod n. Now, what is n? 10. So we will just substitute the values of a and n in the respective places. We get 3 power phi of 10 is congruent to 1 mod 10. Now, if you note here, we are going to find phi of 10. We have already solved this in the previous lecture. Phi of 10 is equal to 4. How did I get this? I hope you can recollect this. I have given some formulas to solve this. See, 10 can be a product of two different prime numbers, 2 and 5, right? So 10 can be written as 2 into 5. So 2 and 5 are two different prime numbers. When you are going to compute phi of n, where n is a product of two different prime numbers pq, the formula is phi of n is equal to p minus 1 into q minus 1. Here 2 and 5 are the prime numbers, so obviously 2 minus 1 into 5 minus 1. So 2 minus 1 is 1 and 5 minus 1 is 4, so 1 into 4 is 4. If you are directly watching this lecture without knowing the basics of phi of n, I request you to watch my previous lectures titled Euler's totient function and Euler's totient function solved examples. So we know the value of phi of 10 is 4, so we are just substituting this value in this place. We get 3 power 4 is congruent to 1 mod 10. And you know how to solve this henceforth because we have already seen enough examples for solving this. I'll directly use the value of 3 power 4, which is 81. So 81 is congruent to 1 mod 10. 81, when it is divided by 10, are we getting 1 as the remainder? Yes, 10 8 times 80, and obviously remainder is 1. So we can conclude that Euler's theorem holds true for a is equal to 3 and n is equal to 10. Let's see example number 2. The question is, does Euler's theorem hold true for a is equal to 2 and n is equal to 10? So we are required, and is congruent to 1 mod 10. 81, when it is divided by 10, this place, we get 3 power 4 is congruent to 1 mod 10. And you know how to solve this to 1 mod 10. 81, when it is divided by 10, are we getting 1 as the remainder? Yes, 10 8 times 80, and obviously remainder is 1. So we can conclude that Euler's theorem holds true for a is equal to 3 and n is equal to 10. Let's see example number 2. The question is, does Euler's theorem hold true for a is equal to 2 and n is equal to 10? So we are required to check whether Euler's theorem holds true for these values. Let's analyze the initial conditions for each other. Case number, true for a is equal to 2 and relatively correct. So we know the 4 to power, when it is divided by 10, we get 6 as the remainder, not 1 as the remainder. So from this, it's clear that Euler's theorem does not hold true for a is equal to 2 and n is equal to 10. The reason is a and n are not relatively prime to each other. Let's see the last example for the day. Example number 3. Does Euler's theorem hold true for a is equal to 10 and n is equal to 11? Let's check whether a and n are relatively prime. Yes, a and n are relatively prime to each other because the GCD of a, n is 1. So let's solve this. We know the given data are a is equal to 10 and n is equal to 11. We know Euler's theorem states that a power phi of n is congruent to 1 mod n when a and n are relatively prime to each other. We will substitute the values. We get 10 power phi of 11 is congruent to 1 mod 11. We are required to find phi of 11, right? So phi of 11 is equal to simply 10. Why? If this n is a prime number, then this is n minus 1, right? So phi of n is equal to n minus 1 if n is a prime number. Here n is a prime number, so we get phi of 11 is equal to 10. We will directly substitute the value. 10 power 10 is congruent to 1 mod 11. Are you going to solve this 10 power 10 using modular exponentiation? We can solve it, we will get the same result anyway, but can you see here, we can simplify this. This is 10 and this is 11. We know this 10 is minus 1 shortage from 11, isn't it? So we can simply write it as minus 1 power 10 is congruent to 1 mod 11, minus 1 to the power odd number, we get minus 1 itself. Since minus 1 power even number we have, we get 1. Now let's check 1 divided by 11. When you divide 1 by 11, we get 1 as the remainder because 11 takes 0 times for 1, so we get 1 as the remainder. So obviously, Euler's theorem holds true for a is equal to 10 and n is equal to 11. Before we sign out, let's see the homework question. The question is, you are required to prove Euler's theorem does not hold true for a is equal to 11 and n is equal to 33. So before progressing with the solution, I request you to check whether a and n are relatively prime to each other. After knowing the answer by looking at the question itself, still you prove this and post your answers in the comment section. And that's it, guys. I hope now you know what Euler's theorem states and the working of Euler's theorem with examples. I hope you guys enjoyed this presentation, and thank you for watching. presentation, we are going to find the primitive roots. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will know about primitive roots of prime number, and we are going to see the Diffie-Hellman key exchange process. There we need the concept of primitive roots, and that's why I am providing the fundamentals here itself. So keep track of this lecture. It will be really helpful for us to solve the problems when we see the Diffie-Hellman key exchange algorithm and problems. While waiting, let's see what is a primitive root. Let's see the definition now. A number alpha is said to be a primitive root modulo n if every number co-prime to n is congruent to a power of alpha mod n. I know the definition seems to be intricate, but I have made the definition easy for you. So let's see the easiest way of saying this. Alpha is said to be a primitive root of a prime number p. So we have a prime number p, and when we will say this alpha is said to be a primitive root of the prime number p, if alpha power 1 mod p, alpha power 2 mod p, alpha power 3 mod p, up to alpha power p minus 1 mod p are distinct. For example, if we are saying a prime number 5, and if we take alpha is equal to 2, so 2 power 1 mod 5, 2 power 2 mod 5, 2 power 3 mod 5, up to 2 power 5 minus 1, that is 2 power 4 mod 5, all are distinct, then alpha is said to be a primitive root of the prime number p. Anyway, we are going to understand this when we see the examples. Let's directly step into example number 1. The question is 2 a primitive root of prime number 5? Here, two important data are given to us. One is the prime number and the other one is 2. So we are required to check whether 2 is a primitive root of the prime number 5. So let's solve this now. So we are going to take 2 power 1 mod 5, 2 power 2 mod 5, up to 2 power 4 mod 5, right? So we are going to solve 2 power 1 mod 5, 2 power 2 mod 5, 2 power 3 mod 5, and 2 power 4 mod 5. And we are going to stop only up to this. Why? Because we are going to stop this up to 2 power 5 minus 1, that is p minus 1. This is what we have seen in the definition. Let's simplify this now. 2 power 1 mod 5 is what? 2 mod 5. Let's come to this. What is 2 power 2 mod 5? 2 power 2 is 4 mod 5, right? So here we get 4 mod 5, here we get 8 mod 5, and here we get 16 mod 5. Let's simplify this. 2 mod 5, 2 when it is divided by 5, obviously 2 is the remainder, right? So we get 2 as the remainder here, so we get 4 as the remainder here, we get 3 as the remainder here. Why? 8 when it is divided by 3, 5 1 times 5, and the remainder will be obviously 3. And 16 when it is divided by 5, we get 1 as the remainder. As per the definition, alpha power 1 mod p, alpha power 2 mod p, up to alpha power p minus 1 mod p should give distinct values, right? Or it should be uniformly distributed, right? When you take this prime number 5, what are all the positive numbers less than 5? It's 1, 2, 3, 4. Are these values uniformly distributed or distinct? Yes, we can see 2, 4, 3, 1, all are distinct values which are uniformly distributed. So 2 is a primitive root of the number 5. So in the question we are asked to find, is 2 a primitive root of the prime number 5? So the answer is yes, 2 is a primitive root of prime number 5. I hope things are clear to you. Let's step into example number 2. In example number 2, we are required to find is 3 a primitive root of prime number 7. Let's solve this now. We know what we are going to do. We are going to check 3 power 1 mod 7, 3 power 2 mod 7, up to 3 power 6 mod 7, right? So we are going to find 3 power 1 mod 7, 3 power 2 mod 7, which is 3 mod 7. When you simplify 3 mod 7, we get 3 as the remainder. Let's move on to the next one. 3 power 2 mod 7, 3 square is what? 9. So 9 mod 7, when you simplify this, we get 2 as the result. What is 3 power 3? So 3 power 3 can be 3 power 2 into 3 power 1, isn't it? We got 3 power 2, which is 2. We got 3 power 1, which is 3. So 3 power 3 can be 2 into 3, right? So 2 into 3 is 6. So we get 6 mod 7. So 6 mod 7 means the remainder is 6. Let's take 3 power 4. 3 power 4 can be written as 3 power 3 into 3 power 1, right? So 3 power 3 is 6, 3 power 1 is 3. So 6 power 3 is 18. So 18 mod 7, we get the remainder as 4. 3 power 5 can be 3 power 4 into 3 power 1. 3 power 4 is 4, 3 power 1 is 3. So 4 into 3 is 12. 12 mod 7 is 5. And finally we get 3 power 6. 3 power 6 can be 3 power 5 into 3 power 1, right? So 3 power 5 is 5, 3 power 1 is 3. So 5 into 3 is 15. So 15 mod 7 will give 1 as the remainder. Are the results distinct? In other words, are the values uniformly distributed? In simple words, are you getting values exactly once? Yes, 3, 2, 6, 4, 5, 1 are appearing only once. or uniformly distributed, or they are distinct? So the answer for this question is yes, 3 is a primitive root of number 7. Let's see the last example. The question is 2 a primitive root of number 7? Now we got the idea of solving this, right? We know we are going to find 2 power 1 mod 7, 2 power mod 7 is 4. See here, this 2, number 7, or simply 4. Power 3 into 2 power 8, when it is divided by 7, we get 1 as the remainder. And also, the results are, it's not a primitive root of prime number. Is 2 a primitive root of prime number 11? So you're required to find 2 power 1 mod 11, 2 power 2 mod 11, up to 2 power 10 mod 11. And if you get the distinct values, then you can confirm 2 is a primitive root of number 11. And question number 2 is, it's a different question. Can you see here, what are the primitive roots of prime number 5? It's not you are going to verify whether the given number is a primitive root or not. You are going to find out what are all the numbers that are primitive root for this prime number 5. So if you want, I can give you a hint for you. The hint is, you can take like this. What are the positive numbers that are less than 5? It's 1, 2, 3 and 4, right? We can ignore this one because 1 power anything will always be 1. So 1 power any positive number will always be 1. So this will not give distinct values or unique values. So let's ignore this. You just ensure with 2, 3 and 4. And already we have solved this in example number 1. We confirm that 2 is a primitive root. Try verifying is 3 a primitive root and 4 a primitive root. So using this hint, I hope you can solve question number 2 also. After solving this, I request you to post your answers in the comment section. And that's it, guys. I hope now you understood what is a primitive root of a prime number, and we also have determined whether a number is a primitive root of a given prime number or not. I hope the session is informative, and thank you for watching. Hello everyone, welcome back. In cryptography, the idea of multiplicative inverse is inevitable, and that is why an exclusive lecture is created for you to help you understand the basics of multiplicative inverse under modular arithmetic. While waiting, let's start the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will know about the multiplicative inverse. Outcome number 2, we will understand multiplicative inverse under modular arithmetic. It means numbers with mod n. And outcome number 3, we will determine whether there exists a multiplicative inverse for a number under modular arithmetic or not. Before diving into what is multiplicative inverse under modular arithmetic, let's understand the basics of multiplicative inverse. Let's take the number 5. So when you have a number 5, when that number is multiplied by its inverse, then we get the result as 1. So it's clear that 1 by 5 is the multiplicative inverse of number 5. So it's clear that when you have a number a, then 1 by a is the multiplicative inverse for number a. So that a, when it is multiplied by its inverse, which is 1 by a, will give 1 as the result. So I am referring this 1 by a as the multiplicative inverse. So this is the basic idea behind multiplicative inverse. But the real challenge comes when modular arithmetic is involved. Say when we are dealing with modular arithmetic, that is when we have a number mod n, then the multiplicative inverse concept will be different. Say if you have a number a, when that number a is multiplied by its inverse, when the multiplication of a and a inverse, when this value is divided by n, we will get the remainder as 1. So this is what the idea of multiplicative inverse under modular arithmetic operations. We have already seen this example previously. 5 is the number, 1 by 5 is the multiplicative inverse. So obviously 5 multiplied by 1 by 5 will be 1, isn't it? So for the number 5, always 1 by 5 is the multiplicative inverse. But when you are finding multiplicative inverse under mod n, there cannot be a fixed number. For example, the multiplicative inverse for 2 mod 5 is different, and the multiplicative inverse for 2 mod 7 is different. You may be thinking like you are going to find the multiplicative inverse for 2 only. But please note, it's not simply 2, it's 2 mod 5 and 2 mod 7. So the multiplicative inverse for 2 mod 5 is going to be a different number, and the multiplicative inverse for 2 mod 7 may be a different number. We need to have an understanding on this. Let's understand things clearly now. Let's say there is a number 3. Now we are going to find the multiplicative inverse of 3. It is 1 by 3 obviously when it is a normal number. But when modular arithmetic is involved, mod 5, right? So what is the multiplicative inverse for 3 mod 5? That's the question is actually. So we are required to find the multiplicative inverse of 3 mod 5. Not simply 3, it's 3 mod 5. So what do you mean by this? I already told you when you have a number, when that number is multiplied by its inverse, we will get 1 as the remainder when this product is divided by n. So similarly, when we have a number here 3, when this 3 is multiplied by its inverse, then the whole result, that is this product, when it is divided by 5, we should get 1 as the remainder. Let's try the number 1. 3 into 1 is 3. So 3, when it is divided by 5, we get 3 as a remainder. So 1 is not the multiplicative inverse for 3. Let's try with 2. 3 into 2. 3 into 2 is 6. So this side we have 6. When 6 is divided by 5, we get 1 as the remainder. So 2 is the multiplicative inverse of 3 mod 5, or 3 is the multiplicative inverse for 2 mod 5. So it's clear that for 3 mod 5, the multiplicative inverse is 2. Let's say we have a number 2, and we are required to find the multiplicative inverse of 2 mod 11. So what's the idea? When this side is divided by 11, we should get 1 as the remainder. What is there in this side? It's the product. So 2 is multiplied by which number? We will get 1 as the remainder when this side is divided by 11. Let's try with 1. 2 into 1 is 2. 2 when it is divided by 11, we get 2 only as the remainder. Let's try 2. 2 into 2 is 4. No. 2 into 3, 6. No. 2 into 4, 8. No. 2 into 5, 10. No. 2 into 5 is what? 10. 10 when it is divided by 11, we get 10 as the remainder or minus 1. But we need plus 1, right? So let's try with 6. So 2 into 6 is 12. 12 when it is divided by 11, we get 1 as the remainder. So the multiplicative inverse of 2 mod 11 is 6. Let's see one more number. 4 is multiplied by what number? We get 1 as the remainder under mod 5. In other words, what's the multiplicative inverse of 4 mod 5? I request you to pause this video for a while and find out 1 as the multiplicative inverse of 2 mod 11 is 6. Let's see one more number. 4 is multiplied by what number? We get 1 as the remainder under mod 5. In other words, what's the multiplicative inverse of 4 mod 5? I request you to pause this video for a while and find out what's the multiplicative inverse for the number 4 mod 5. I hope you are done. Let me reveal the answer for this. So 4 when it is multiplied by 4, we get 16. This 16 when it is divided by 5, we get 1 as the remainder. So 4 is the multiplicative inverse for 4 mod 5. Do we have a multiplicative inverse for this? 5, when it is multiplied by its inverse, we should get 1 as the remainder when this whole side is divided by 10. Just try here 5 into 1. 5 into 1 is what? 5. So 5 when it is divided by 10, we get 5 as the remainder. Let's try with 2. 5 into 2 is 10. 10 when it is divided by 10, we get 0 as the remainder, not 1. When you try 3, we get 5 as the remainder. When you try 4, you get 0 as the remainder. So in this case, you will never get a multiplicative inverse if you start applying all the numbers. Do you agree with me? You know why it is so? Because this 5 and 10 are not relatively prime. So multiplicative inverse exists only when this number and this number are relatively prime to each other under modular arithmetic. So in this case, 3 and 5 are relatively prime to each other, and that is why we have a multiplicative inverse here. Similarly, when you take this number 2 and 11, so 2 and 11 are relatively prime to each other. In other words, GCD of 2 and 11 is 1, and that is why there exists a multiplicative inverse for 2 mod 11. Similarly, there exists a multiplicative inverse for 4 mod 5, because 4 and 5 are relatively prime to each other. In other words, GCD of 4, 5 is 1, and that's why there exists a multiplicative inverse. If the GCD of two different numbers is not 1, then it means they are not relatively prime to each other. In such cases, we will never have a multiplicative inverse. So in this example, we can clearly say that 5 mod 10 will not have a multiplicative inverse. You know why? Because 5 and 10 are not relatively prime to each other. The GCD of 5, 10 is 5, and hence we can say that 5 mod 10 does not have a multiplicative inverse. So in the initial part of this lecture, I told you the multiplicative inverse of 2 is 1 by 2. But the multiplicative inverse of 2 mod 5 and the multiplicative inverse of 2 mod 7 are different. That's what I told you. It's not simply 2, it's 2 mod 5 and 2 mod 7. Let's understand that now. See here, the multiplicative inverse of 2 mod 5 is 3. Why? 2 when it is multiplied by 3, we get 6, right? So 6 when it is divided by 5, we get 1 as the remainder. So the multiplicative inverse of 2 mod 5 is 3. But the multiplicative inverse for 2 mod 7 is 4. You know why? 2 into 4 is 8. 8 when it is divided by 7, we get 1 as the remainder. Now if you try 3, 2 into 3 is what? 6. So 2 when it is divided by 3, we get 6 as the remainder. 6 mod 7 or minus 1, isn't it? 3 is not the multiplicative inverse here, where 4 is the multiplicative inverse for 2 mod 7. And that is why I told you multiplicative inverse always vary based on this number, that is the modular number. If you are asked to find the multiplicative inverse for smaller numbers, you can easily start from 1 if 1 is a multiplicative. Inverse or 2 or 3, and you can go ahead and do that. Think if the numbers are big or the prime number is a big prime number. Then obviously you can't manually go and try this. Let's say if the multiplicative inverse is 40,095. Do you think manually trying from 1 to 40,095 is easy for you? So obviously we need some algorithms to help us to find the multiplicative inverse easily. The algorithm is the extended Euclidean algorithm. In the coming lectures, I will solve some problems for finding the multiplicative inverse using extended Euclidean algorithm. And that's it guys. I hope now you know about the multiplicative prop for 40,095. Do you think manually trying from 1 to 40,095 is easy for you? So obviously we need some algorithms to help us to find the multiplicative inverse easily. The algorithm is the extended Euclidean algorithm. In the coming lectures, I will solve some problems for finding the multiplicative inverse using extended Euclidean algorithm. And that's it guys. I hope now you know about the multiplicative inverse, and we also have understood about multiplicative inverse mod n, and we also have determined whether there exists a multiplicative inverse for a number and a modular arithmetic or not. I hope you guys enjoyed this presentation, and thank you for watching. We have seen the basics of multiplicative inverse in the last presentation. In this presentation, we will focus on finding the multiplicative inverse using extended Euclidean algorithm. Let's see solved example 1. While solving this example, we will understand how this extended Euclidean algorithm works. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will know about multiplicative inverse, and outcome number 2, we will determine the multiplicative inverse of a given number under mod n using extended Euclidean algorithm. From the last presentation, we understood what is multiplicative inverse, and we also have seen how to find multiplicative inverse manually for smaller numbers under modulus. So when small numbers are given, it's easy to find the multiplicative inverse. Think if the number is a big number. Obviously, we need some algorithm, right? For that, we are going for the extended Euclidean algorithm. So we are here to find the multiplicative inverse using extended Euclidean algorithm. Now, if you see here, I'm going to explain this in the tabular column approach. Just recollect the lecture finding GCD method 1. In method 1, what 4 columns we had? The first column is the quotient, then A, B, and the remainder. So we had only these 4 columns when we solved some problems using Euclidean algorithm. To be precise, method 1 of Euclidean algorithm. Now we are going to extend this Euclidean algorithm, and that is why it is named as extended Euclidean algorithm. What is the extension we are making? We are additionally including 3 more columns, T1, T2, and T. Don't worry about all the columns. Anyway, when we solve the example problem, we will understand things clearly. Now, as usual, we have a set of prerequisites. The points to ponder include the first point is A should be greater than B. And we are very well aware of this because already while solving the problem of GCD, we understood that A should be greater than B. And we know how to fill this Q and R. So after placing the values of A and B, we know how to fill the values of Q and R. It's so simple, A mod B we are going to perform. So we are going to divide A by B. Obviously, we'll be getting some quotient and remainder. Quotient value will be placed here and the remainder value is going to be placed here. We are very clear about this because already we have seen this in the GCD method 1 using Euclid's algorithm. What are the new things here? The new things here introduced are T1 and T2. For the first iteration or for the first time, T1 and T2 values are 0 and 1 respectively. So when you are dealing with the first row, place 0 in T1 and 1 in T2. Then we are going to compute T. I'm just giving the formula for T. T is equal to T1 minus T2 into Q. So you just use this formula. Don't worry about this. Anyway, I'm not going to explain how we get this because we are going to just use this extended Euclidean algorithm to find the multiplicative inverse, and this is not a mathematics class. So just use this formula. T is equal to T1 minus T2 into Q. So obviously the first row will be filled, right? After completing the iterations, you will be encountering a situation where you cannot move further or you cannot proceed with the algorithm further. In that case, so whatever is there in T1, that is going to be the multiplicative inverse. I hope things are clear. If things are not clear, no worries. When we see the example, you will understand this easily. So as mentioned, when you find a situation where you cannot proceed with the division further, then that moment, so whatever is there in T1, that is going to be the multiplicative inverse that you are looking for. So let's see the example now. Example number 1. What is the multiplicative inverse of 3 mod 5? As already mentioned in the previous lecture, there exists a multiplicative inverse only when this value and this value are relatively prime to each other. Since 3 and 5 are relatively prime to each other, we can definitely say there exists a multiplicative inverse. Let's solve this now. We know the solution includes 7 columns, Q, A, B, R, which we had in the Euclid's algorithm way of computing GCD, and we are extending this Euclid's algorithm like T1, T2, and T. As already mentioned, A should be taking the bigger value, right? So 3 and 5, what is the bigger value? 5. So 5 is placed in A and 3 is going to be placed in B. Now we are going to do a simple computation, that is the division operation, A mod B. When we perform A mod B, 5 divided by 3, 3 1 times 3, and the remainder is 2. So we are just going to fill this quotient in which place? This place. And this remainder in this place, right? So we are going to fill 1 in the quotient and 2 in the remainder. Now, as already mentioned, for the first row, the value of T1 and T2 are set. So T1 is equal to 0 and T2 is equal to 1. So I'm just filling T1 is equal to 0 and T2 is equal to 1. And we know how to compute T, right? This is the formula. So when we use this, T is equal to T1, we know it is 0. T2, it is now 1. So 0 minus 1 into 1. So when we evaluate this, we get 0 minus 1. Finally, we get T is equal to minus 1. I'm going to take and place this value here. So we get T is is equal to -1. So first row is over. Then what we need to do? Just recollect what we did in Euclid's algorithm. We did shifting operation, right? So the same shifting we are going to perform. Whatever the value of b, that is going to be stored in a. Whatever the remainder is, that is stored in b, right? So the value of b is shifted to a, and the value of r is shifted to b. We did only this in Euclid's algorithm, but we are going to do something additionally here, which is the value of t2 is placed in t1 and the value of t is placed in t2. So if you remember this, that's it. You can easily solve this problem. Now a is going to store 3, b is going to store 2, t1 is going to store 1, and t2 is going to store -1. So now repeat the algorithm. What we are going to do a mod b, right? When you do a mod b, 3 divided by 2, 1 times 2, the remainder is 1. Here quotient is 1, remainder is 1. So quotient is 1 and remainder is 1. I've completed filling this detail. Now we are going to compute the value of t. For this, we are not going to take 0 and 1 for t1 and t2 respectively, because this is only for the initial condition. Now we have the value of t1 and t2, right? So we are going to use this value. Now we are going to take this formula and apply what's the current value of t1. It is 1, right? So t1 is 1 minus t2. T2 is -1 into what is q? Q is 1. So I'm taking this value. When you evaluate this, you get t is equal to 2. I hope things are clear. So I'm just going to take this value and going to place this here. So I'm just filling 2 here. So the second row is also filled. Are we able to proceed with the algorithm? Yes, let's see. So what we are going to do? We are going to do the shifting operation. Let's start the shifting. So a takes this value and b takes this value, right? Similarly, taking their respective place. At 1 to t2 is 2. So just apply this value -1, 2, and 2. Why this 2? Because the quotient value right now here. So we are just substituting the values and evaluating this. We get t is equal to -5. And just placing this value in the appropriate place. So third row is also complete. Let's proceed with the algorithm further. So whatever is there in b, it is assigned to a. Whatever is there in the remainder, it is assigned to b. Similarly, whatever is there in t2 is given to t1, and whatever is there in t is given to t2. That's fine. Let's run the algorithm again. So a mod b. So 1 divided by 0. Obviously, we are encountering a situation where we cannot move further or proceed further. So this is the place where we are going to stop. So we cannot determine the quotient or the remainder or even the value of t, because q is not known here, right? So this is a place where we are stopping. Now, when you are stopping this algorithm, whatever is there in t1, what's the value that is there in t1? 2. So that's the answer for this question. That's the multiplicative inverse. So it's clear that 2 is the multiplicative inverse of 3 mod 5. If you want to verify, just take this value 3 into 2. When a number is multiplied by its inverse, then the whole value is divided by this mod. You should get 1 as the remainder, right? That's what the logic of multiplicative inverse. So 3 is the number, 3 into 2 is 6. 6 when it is divided by 5, we get 1 as the result. So 2 is the multiplicative inverse of 3 mod 5. I hope things are clear to you. And that's it, guys. I hope now you have the understanding about multiplicative inverse in depth, and we also have determined the multiplicative inverse of a given number under mod n using extended Euclidean algorithm. I'll inverse index of 3 mod 5. I hope things are clear to you. And that's it, guys. I hope now you have the understanding about multiplicative inverse in depth, and we also have determined the multiplicative inverse of a given number under mod n using extended Euclidean algorithm. I'll meet you with different numbers in the next presentation. Until then, thank you for watching. It's here that we are going to extend the Euclid's algorithm, which we use q a multiplying to find the multiplicative inverse of 11 mod 13. So let's solve this now. We know the solution is going to take these 7 columns, and let's fill the biggest number in a, the smallest number in b. So it's clear that 13 is going to be stored in a and 11 is going to be stored in b. So let's start the division operation. 13 mod 11. So 11 1 times 11 and the remainder is 2. So the quotient is 1 and the remainder is 2. We know the values of t1 and t2 at the initial stage. It's clear that t1 is equal to 0 and t2 is equal to 1. So we are filling 0 in t1 and 1 in t2. T is actually t1 minus t2 into q. So we will substitute the value t1 is 0, which is this, t2 is 1, which is this. After substituting the values, after evaluating, we get t is equal to -1. So the current value of t is -1, the first row is over. Now what we are going to do? The shifting. So a takes the value of b, b takes the value of the remainder. T1 takes the value of t2 and t2 takes the value of t. So just move 11 to a and 2 to b. Similarly 1 to t1 and -1 to t2. So when you shift the values, you will be getting the rectangle filled up like this. I hope things are clear. Now perform the division operation. You are going to perform 11 mod 2, right? So you are going to divide 11 by 2. 2 5 times 10 and the remainder is 1. The quotient is 5 and the remainder is 1. Now you know how to compute t. You are not going to use 0 for t1 and 1 for t2. Now we have t1 and t2 with the values, right? So t is equal to t1 minus t2 into q. We will get t is equal to 1 minus -1 into 5. So So just refer this row for the values. Now after evaluating this, we get t is equal to 1 plus 5, which is equal to 6. Now we found out the value of t, which is 6. Now second row is also over. What we are going to do? The shifting operation. So the shifting operation continues. So whatever is there in B, that is going to be stored in A. Whatever is there in the remainder, it is going to be stored in B. Similarly, whatever is there in T2, it is going to be stored in T1, and whatever is there in T, it is going to be stored in T2. Now we can witness that the values are being filled up appropriately. I hope things are clear as of now. Now what we are going to do? We are going to do the division operation. So we are going to perform 2 mod 1, right? So when you perform 2 mod 1, you get 2 as the quotient and 0 as the remainder. So now the quotient is going to be 2 and the remainder is going to be 0. Now calculate the value of t. So t is equal to t1 minus t2 into q. You know t1 is minus 1, t2 is 6, and q is 2. Just substitute the values and evaluate this. You get t is equal to minus 13. Let's fill that here. Now, is the algorithm going to stop? No, it's going to continue. So let's continue the algorithm. Obviously, the value of b is given to a, and the value of the remainder is given to b, and then t2 is given to t1, and t is given to t2. Now you can see the values are being filled up appropriately. At the end of this operation, we get the table filled up like this. Now the next step is doing a mod b operation, right? So when we do a mod b operation, we are not able to perform because we are encountered with the situation divide by 0. So obviously there can be no quotient or no remainder, and t value is also unknown. In this stage, whatever is there in t1, that is going to be the multiplicative inverse, right? So 6 is the multiplicative inverse of 11 mod 13. Let's verify this. So 6, when it is multiplied by 11, we get 66. 66 when it is divided by 13, 13 5 times 65, and obviously the remainder is 1. Therefore, 6 is the multiplicative inverse of 11 mod 13. Before we sign out, let's see the homework question. The question is, what is the multiplicative inverse of 10 mod 11? I request you to solve this problem and post your answers in the comment section. And that's it, guys. I hope now you know about multiplicative inverse. We also have determined the multiplicative inverse of a given number under mod n using extended Euclidean algorithm. I hope the session is informative, and thank you for watching. Hello everyone, welcome back. In this presentation, we will see solved example number 3 in multiplicative inverse using extended Euclidean algorithm. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will know about the multiplicative inverse, and outcome number 2, we will determine the multiplicative inverse of a given number under mod n using extended Euclidean algorithm. We know very well how we are going to find the multiplicative inverse. Here we are going to apply the extended Euclidean algorithm. The algorithm goes like this. We have 7 columns, Q, A, B, R. These are the 4 columns we have in the Euclid's algorithm, and we are going to have 3 more columns, T1, T2, and T. Obviously, we are going to find multiplicative inverse under mod n. So obviously, we'll be having 2 numbers. The biggest number is placed in A and the smallest number is placed in B. So that's the first point. Then we are going to perform A mod B operation. The result of this A mod B operation will give 2 results. One is the quotient and the other one is the remainder. We are going to place the quotient here and the remainder here. In the first step of the calculation, we are going to use T1 and T2 as 0 and 1 respectively. So T1, T2 values will be filled, and we are going to T using this formula. T is equal to T1 minus T2 into Q, and we are going to run this algorithm till we encounter a situation where the division of A mod B cannot be performed. In that state, whatever we have in T1, that's the multiplicative inverse. With this knowledge, let's see example number 3. The question is, find the multiplicative inverse of 11 mod 26. So there are 2 numbers given here. One is 11 and the other one is 26, and we want to find the multiplicative inverse of 11. So 11 is multiplied by its inverse. When that result is divided by 26, we should get the remainder as 1. What's that number? That's what we are going to find. We know we are going to use the extended Euclidean algorithm, which has these 7 parameters. Now, the given inputs are 11 and 26. Which is the biggest number? 26. So 26 is placed in A and 11 is placed in B. And what's the next step? We are going to perform A mod B. So we are going to perform 26 mod 11. When we perform the division, we get the quotient as 2 and remainder as 4. And we are going to place this in the appropriate places against quotient and remainder. We know in the first round we are going to use T1 is equal to 0 and T2 is as minus. Let's proceed with step number 2. So we are going to do the shifting operation. So the value of B is stored in A and the value of the remainder is stored in B. Similarly, the value of T2 is stored in T1 and the value of T is stored in T2. So when we do this operation, we can see the table is getting filled like this. Now repeat the same A mod B operation. Now A is 11, B is 4. So when we do this A mod B operation, we get the quotient as 2 and the remainder as 3. And we also compute the value of T is equal to T1 minus T2 into Q. Now we have T1, T2 with their own values, which is 1 and minus 2 respectively. Using this value, we are going to compute the value of T, which is equal to 5 in this case. So I'm just filling 5 against T. Are we going to stop this algorithm? No. Let's proceed with the algorithm, moving value of B to A and the remainder to B. Similarly, T2 to T1 and the value of T to T2. So obviously, we'll be getting the table like this. Now we are going to perform the same A mod B. When we are doing this value like this and we are going to perform A mod B, we get the quotient as 3 and the remainder as 0, and the value of T is computed as 26. And T1 is equal to minus 7 and T2 is equal to 26. Let's do A mod B operation. Obviously, we are encountering a situation divide by 0. It cannot be proceeded further. So we are stopping this algorithm up to this. So when we encounter a situation divide by 0, whatever is there in T1, that's the multiplicative inverse. So the multiplicative inverse of 11 mod 26 is minus 7. But just recollect this, I told you always have the final result in positive. So how can we make it positive? So it means minus 7 is the multiplicative inverse of 11 mod 26, which is perfectly fine. But we want a positive number. This minus 7, in other words, it is minus 7 mod 26. When we have minus 7 mod 26, just add minus 7 and 26, we get a positive number. So minus 7 plus 26 is equal to 19. So it's clear that 19 is of 11 mod 26. Please be advised that the multiplicative inverse exists only when these two numbers are relatively prime. In other words, the GCD of these two numbers is 1. In this example, we have taken 11 mod 26. It means GCD of 11, 26 or GCD of 26, 11 is equal to 1. That means 1 is the only number that can divide both 11 and and 26. So that's what I mentioned as 11 and 26 must be relatively prime. Only then there exists a multiplicative inverse. So when you work with this algorithm, please be ensured that the GCD of these two numbers what is given in the question is 1. In other words, they should be relatively prime to each other. And that's it guys. I hope now you understood multiplicative inverse and we also know how to find the multiplicative inverse of a given number which is having mod n using extended Euclidean algorithm. I hope the session is informative and thank you for watching. Hello everyone, welcome back. In this presentation, we will focus on understanding the Chinese remainder theorem and we will also solve example number 1 in Chinese remainder theorem. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the working of Chinese remainder theorem with an example. Let's directly dive into the topic of the day, the Chinese remainder theorem. Let me tell you the theorem first. The Chinese remainder theorem, simply CRT, is used to solve a set of different congruent equations with one variable but different moduli which are relatively prime. It means we are going to have a set of different congruent equations. It's clear that these congruent equations are different but with only one variable and different moduli. So we are going to find the value of this one variable using Chinese remainder theorem. I know things will be a little bit not clear for you at this stage. Anyway, when we see some examples, you will understand this. Before that, let's have a theoretical understanding. So we have different congruent equations as mentioned in the definition, where x is congruent to a1 mod m1, x is congruent to a2 mod m2. We have n equations, x is congruent to an mod mn. If you see here, we have one variable which is x here, right? And we have a set of different congruent equations, which is this. We have n different congruent equations. And if you note here, there are different moduli. This is mod m1, this is mod m2, this is mod mn. We have n different equations with different moduli, different a values, but the variable is 1. Now we are going to find the value of this single variable. Let's see what this Chinese remainder theorem states. So Chinese remainder theorem states that the above equations have a unique solution of the moduli are relatively prime. So m1, m2 up to mn, when they are relatively prime to each other, then there exists a unique solution x. I hope the theorem is clear for you. If not clear, no worries. Let's solve example number 1 and you will understand things clearly. Before diving into example number 1, what is the formula for finding this value of x? So the value of x can be x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse up to an mn mn inverse mod capital M. If you note here, few values are available. On the question. A1, A2 up to AN can be taken from the question, and we are required to calculate the other unknown variables, including this mod m, using the values that are available in this set of congruent equations. So this is the equation which is used to find the value of x. Let's see example number 1. Solve the following equations using Chinese remainder theorem. The equations are x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. How many equations are given in this question? 3 equations. So we are going to modify the formula in such a way that it is going to cater 3 different congruent equations. You can adjust the formula according to the need. Let's solve this now. We are going to have the equation like x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse plus a3 m3 m3 inverse whole mod m. Why we are stopping up to m3? Because we have 3 equations, 1, 2 and 3. If you have 4 equations, then add plus a4 m4 m4 inverse mod m. So it's so simple. Since we have 3 equations mentioned in the question, our formula goes like this. Now let's see what are the given data. In order to find the given data, let's see this with the comparison. We know Chinese remainder theorem, we have different congruent equations like this. X is congruent to a1 mod m1, x is congruent to a2 mod m2, and x is congruent to a3 mod m3. Since we have 3 different equations in the question, I'm stopping up to this. And what's the given data in the question? It's x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Let's compare these two so that we can find the given data. So we know this is the equation we are going to apply, and the given data are a1 is 2, a2 is 3, and a3 is 2. So that's what we have mentioned here. A1 is 2, A2 is 3, and A3 is 2. Then what are all the other given data? Small m1, small m2, and small m. In other words, GC can say 3, but there is no small m1 here. We have capital M1 inverse, capital M2, capital M. We are required to find capital M1, capital M2, which is the given data are A1, A2, A3, small m1, small m2, small m3. Let's find capital M1, capital M2, capital M3, and their corresponding inverse, also capital M. To find capital M, it's so simple. It's the product of all these small m's. No, which is given data are also small m3, right? So capital M is the product of small m1, small m2, and small m3. So when we substitute this, we get capital M is equal to 3 into 5 into 7, which is equal to 105. So we found the value of capital M, which is 105 here. We are done with finding capital M. Let's now move on to find capital M1, capital M2, and capital M3. So let's navigate to finding capital M1, capital M2, and capital M3. How to deal with this? So we are going to find 3 values, capital M1, capital M2, and capital M3. So the formula is capital M1 is equal to capital M upon small m1. That is what we have found here, capital M upon small m1. Similarly, capital M2 is equal to capital M upon small m2, and capital M3 is equal to capital M upon small m3. We know the values of capital M and all small m values, right? We will just substitute it here. So when we simplify this, we get capital M1 as 35 and capital M2 as 21. Why 21? Because capital M is 105 and small m2 is 5, which is this. So we get capital M2 as 21 and capital M3 as 105 upon 7. Why 7? Because small m3 is 7. So when we substitute this value, we get capital M3 is equal to 15. Now we have found out the values of capital M1, capital M2 and capital M3, which is 35, 21 and 15 respectively. So we have done finding most of the values. So now we are required to find capital M1 inverse, capital M2 inverse and capital M3 inverse. The formula for finding capital M1 inverse, capital M2 inverse and capital M3 inverse are projected here. It's so simple. We know capital M1, right? So we are going to find the multiplicative inverse of this capital M1. So when capital M1, when it is multiplied by its multiplicative inverse, we should get remainder 1 when we perform with mod small m1. Please focus on this row. So when this value is multiplied by its inverse, we will get 1 as the remainder under mod m1. Similarly, capital M2 is multiplied by capital M2 inverse will give 1 under mod small m2. Similarly, capital M3 is multiplied by capital M3 inverse will give 1 under mod M3, which is small m3, which is this. So we will substitute the values what we have found. So let's focus on finding capital M1 inverse. So we substitute M1 to be 35 because that's what we have found it in the previous step. So we have 35 is multiplied by capital M1 inverse will give 1 mod 3. Why 1 mod 3? Because small m1 is 3. Now you can go for extended Euclidean algorithm to find the multiplicative inverse, or you can start applying from the values 1, 2, 3 till you get the final result. So let's start with 1. When capital M1 inverse is 1, 35 into 1 is 35. Then 35 when it is divided by 3, are you getting 1 as the remainder? 35 when it is divided by 3, you get 2 as the remainder. So M1 inverse is not 1. Let's try 2. So 35 into 2 is 70. 70 when it is divided by 3, we get 1 as the remainder. So we have M1 inverse as 2. We easily found it out because all these values are small numbers, so I'm not going for extended Euclidean algorithm for solving this. If the numbers are big, I want you to find the multiplicative inverse using extended Euclidean algorithm. If you are not sure about this extended Euclidean algorithm for finding the multiplicative inverse, I request you to watch my previous lectures. We are done with finding capital M1 inverse. Let's now move on to capital M2 inverse. So we know capital M2 is multiplied by capital M2 inverse will give 1 mod small m2. So we will substitute the values here. Now let's start applying 1 to capital M2 inverse. If we use M2 inverse as 1, 21 into 1 is 21. 21 when it is divided by 5, we get 1 as the remainder. Yes, it's perfect. So we know capital M2 inverse is 1, and we will move on to the next step, finding capital M3 inverse. We will apply the value. Capital M3 is equal to 15, which is this. Now 15 is multiplied by what? We will get 1 as the remainder when it is divided by 7. Let's apply 1. So 15 when it is divided by 7, we get 1 as the remainder. So M3 inverse is also 1 in this case. So we have found out the values of capital M1 inverse, capital M2 inverse and capital M3 inverse. We will substitute the values. So now we got all the values that are required to find the value of x. Alright, we know how to find the value of x, which is this. So it's clear that we have all values that are required to be placed here x. Alright, we 3 inverse. We will substitute the values. So now we got all the values that are required to find the value of x. Alright, we know how to find the value of x, which is this. So it's clear that we have all values that are required to be placed here so that we can evaluate this expression and find the value of x. Let's solve it now. So the given question is here and we are going to solve x is equal to a1 capital M1 inverse plus a2 capital M2 inverse plus a3 capital M3 inverse the whole mod m. I'll bring the table from the previous slide. So this is the value. I'm going to take this and place it here. Alright, now let's substitute the values here. So we get this expression. Just fill these values from this table. Now when you evaluate this, you get 233 mod 105. Why 105? Because capital M, which is 105 here. So when you evaluate this, you get 23 as the remainder. So finally, we got the value of x to be 23. So we found out 23 is congruent to 2 mod 3, 23 is congruent to 3 mod 5, 23 is congruent to 2 mod 7. Is this correct? Let's verify this. Let's take the first equation. 23 is congruent to 2 mod 3. 23 when it is divided by 3, are you getting 2 as the remainder? 3 7 times 21, we get 2 as the remainder. It's matching. Perfect. Let's move on to the second equation. 23 is congruent to 3 mod 5. So 23 when it is divided by 5, are you getting 3? Yes. 5 4 times 20, remainder is 3. So this is also perfectly fine. Let's move on to the third equation. 23 is congruent to 2 mod 7. 23 when it is divided by 7, 7 3 times 21 and the remainder is 2. Perfect. So we found out the value, that is the single variable x, to be 23, and we also have verified the result. So Chinese remainder theorem is helping us to solve the different congruent equations under one variable. Please be noted that only one condition. The condition is these moduli values should be relatively prime. Only then we will get the correct result. I hope things are clear to you now. And that's it guys. I hope now you understood the working of Chinese remainder theorem with an example. I'll see you in the next presentation. With a different example of Chinese remainder theorem, and thank you for watching. In the last presentation, we understood what is Chinese remainder theorem, and we have seen solved example number 1 in Chinese remainder theorem. In this presentation, we will solve another example in Chinese remainder theorem. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the working of Chinese remainder theorem for diving into the quest find the common variable x, but we have different moduli m1, m2 up to mn. Only one condition, these moduli should be relatively prime. If this is the case, then we can easily find the common up to plus an capital M n inverse mod capital M. If we have 3 equations, we will take 3 parts. If we have 4 equations, we will take 4 parts. It depends upon the question. Let's dive into example number 2 now. The question is, solve the following equations using Chinese remainder theorem. The equations are 4x is congruent to 5 mod 9 and 2x is congruent to 6 mod 20. We are required to solve these two congruent equations and we are required to find the value of x. In the last example we have solved, we are given with the question which is directly x is congruent to. But here this is 4x and this is 2x. So a small trick is applied on the question here. No worries, we will break the trick first and then we will proceed with solving these congruent equations. Let's break the trick now. So we are going to rewrite the question as follows. We have two equations, right? So I'm going to take two columns. Let me place the first equation here and let me place the second equation here. So here we want to make it as x is congruent to something mod 9. Here we are going to rewrite it as x is congruent to something mod 20. So if you want to make here x, what we need to do? We need to multiply by 4 inverse, right? Is it okay to multiply 4 inverse only on one side? No, that will affect the equation. So we are going to multiply 4 inverse on both the sides. So when we multiply by 4 inverse on both the sides, we get the equation as this side 4 inverse into 4x, which is this, then 4 inverse multiplied by 5, which is this, mod 9. So 4 inverse into 4, obviously it gets nullified, we get x. But here we need to solve this 4 inverse. So as mentioned, this side we get x, this side we have 4 inverse into 5 mod 9. So we are required to find what is 4 inverse mod 9. Because this mod 9 is applicable for 4 inverse as well. So we are going to find the multiplicative inverse of 4 mod 9. We will start applying with 1. 4 into 1 is 4, 4 mod 9 is 4, not 1. Because when a multiplicative inverse, when it is multiplied with that number, we should get 1 as the remainder. But in this case, 1 is not the multiplicative inverse. Let's try with 2. 2 into 4 is 8. When 8 is divided by 9, we get 8 as the remainder, not 1. Let's try 3. 4 into 3 is 12. 12 mod 9 is 3. Let's try 4. 4 into 4 is 16. 16 mod 9, we get 7. Let's try 5. 4 into 5 is 20. 20 mod 9, we get 2. Let's try 6. 6 into 4 is 24. 24 mod 9. What we will get? We get 6, right? So let's try 7. 4 into 7 is 28. 28, when it is divided by 9, we get 1 as the remainder. So we are going to find the multiplicative inverse of 4 mod 9. You can manually try this or you can refer my previous lecture to find out the multiplicative inverse using extended Euclidean algorithm. 7 is the multiplicative inverse of 4. So 4 into 7 is 28. 28 mod 9. 28, when it is divided by 9, we get 1 as the remainder. So 7 is the multiplicative inverse of 4 mod 9. Then we have this 5 mod 9 here. I'm just retaining this here. We get 7 into 5 mod 9. What is 7 into 5? It is as the remainder. You can take either this or this. I always recommend you to go for smaller numbers. So 35 mod 9 can be reduced as 8 mod 9. Just divide 35 by 9. 9 3 times 27 and the remainder is 8. So we are reducing this as x is congruent to 8 mod 9. But this side it's so simple. Why? Because here we have 2. Here also we have a number that can be divided as x is congruent to 8 mod 9. But this side it's so simple. Why? Because here we have 2. Here also we have a number that can be divisible by 2. So we can rewrite the 6 as 2 into 3, right? So 2x is congruent to 2 into 3 mod 20. When we divide by 2 on both the sides, we get x is congruent and x is congruent to 3 mod 20. Let's solve this question using these two congruent equations. Now we have simplified the question in the format x is congruent to a1 mod m1 and x is congruent to a2 mod m2. Please note here we have only two different congruent equations. Let's solve this question now. In order to find the value of x, we know the formula is x is equal to a1 capital M1 inverse plus a2 capital. We can easily find the given data. We have only two congruent equations, so I'm just comparing the equation with the question. So what's the given data? A1 is 8 and a2 is 3. So a1 is equal to 8, a2 is equal to 3. And small m1 is 9 and small capital M1 capital product of small m1 and small m2. So m is equal to m1 into m2. Please note these are small m 100 on small capital M2 is equal to capital M upon small m2. If you're directly watching this lecture, I request you to watch my previous lecture, solve example 1, so that you will get a better insight about Chinese remainder theorem and how to solve 2 of inverse and m. We get 1 as the remainder when we do mod small m1, right, which is this. So capital M1, when it is multiplied by capital M1 inverse, we get 1 as the remainder under mod small m1. Similarly, capital M2, when it is multiplied by capital M2 inverse, we get 1 mod small m2. We know what is the value of capital M1 and capital M2. So firstly, let's focus on this equation. We get 20 into capital M1 inverse is equal to 1 mod 9, because small m1 is 9, which is this. So 20 into what we get, the whole product when it is divided by 9, we get 1 as the remainder. Let's start applying with 1. You can also go for extended Euclidean algorithm to find the multiplicative inverse. Since these are all smaller numbers, I'm going directly. Let's try with 1. 20 into 1 is 20. 20 when it is divided by 9, we get 2 as the remainder. So 1 is not the multiplicative inverse of 20 mod 9. Let's try 2. 20 into 2 is 40. No, we don't get 1 as the remainder when we divide 40 by 9. Let's try 3. No. Let's try 4. No. Let's try 5. Yes. 20 into 5 is 100. 100 when it is divided by 9. 9 11 times 99. So we get 1 as the remainder. So obviously capital M1 inverse is 5. That's what we obtained. Let's move on to the second part, which is this. We know what is the value of capital M2, which is 9. So I'm placing this 9 here, and we know what is small m2, which is 20 here. So 9 into what? We will get 1 as the remainder when it is divided by 20. So let's try with 1. No. 2. No. 3. No. 4. No. 5. No. 6. No. 7. No. 8. No. 9. 9 into 9 is 81. 81 when it is divided by 20, 24 times 80, we get the remaining values in the table. So we have found out all the question or x congruent to 8 table. So when we evaluate this, we get 143 as the value of x. It means 1043 when it is divided by 180, we get 143. When 143 when it is divided by 9, we get 8 as the remainder, and 143 when it is divided by 20, we get 3 as the remainder. So we have verified the final result also. So we have found out x is equal to 143. Before we sign off, let's see the homework question. The question is, solve the following equations using CRT. The equations are x is congruent to 5 mod 3, x is congruent to 2 mod 5, and x is congruent to 1 mod 11. Please note here 3, 5, 11 are relatively prime to each other. Hence, there exists a unique solution for this question. I request you to solve this question and post your answers in the comment section. And that's it, guys. I hope now you understood the working of Chinese remainder theorem with an example. Hello everyone, welcome back. In this presentation, presentation, we will understand the discrete logarithm problem. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the discrete logarithm problem, and outcome number 2, we will know about one-way function and its prime. Before understanding what is discrete logarithm problem, let's see an analogy. Say if you like coffee, just think of how can we make a coffee. To make coffee, we obviously need milk, right? So let's take we have taken a milk and also we need some coffee powder, isn't it? When we have the right items, obviously we can prepare coffee which we like. So it's very easy to prepare the coffee, isn't it? So this is easy in one direction. Just think of the reverse situation. You are given with the coffee and you are asked to estimate the exact quantity of milk and coffee powder used to prepare that coffee, which is certainly a difficult task. So it is not easy in the reverse direction. So what I mean to say here is preparing the coffee is easy in one direction, but the reverse is hard. Please make a note of this analogy. I will link this analogy with discrete logarithm problem in the later part of this presentation. So for time being, we are just putting a pause to this analogy and we are moving forward towards understanding the discrete logarithm problem. We know very well this modular arithmetic is also called as clock arithmetic. Let's take a prime number 17. Just imagine there is a clock with 17 units. So we can see that the clock is from 1 to 17, where 17 is a prime number. And we are taking a number called 5. Can you see here the number 5 power 1 more 17, 5 power 2 more 17, up to 5 power 16 more 17 is performed. Can you just recollect what concept is this? Just recollect the concept of primitive roots. What did we do there? We took a prime number and we took the primitive root of this prime number. If 5 is a primitive root of the prime number 17, then 5 power 1 more 17, 5 power 2 more 17, up to 5 power 16 more 17. That is, if 17 is the prime number which is denoted as p, then 5 power p minus 1 mod p, that is 5 power 16 more 17, will give unique result. Let's start with 5 power 1 more 17. 5 power 1 more 17 is 5. 5 power 2 more 17 is 8. 5 power 3 more 17 is 6. 5 power 4 is 13. 5 power 5 more 17 is 14. 5 power 6 gives 2. 5 power 7 gives 10. 5 power 8 gives 16. 5 power 9 gives 12. 5 power 10 gives 9. 5 power 11 gives 11. 5 power 12 gives 4. 5 power 13 gives 3. 5 power 14 more 17 gives 15. 5 power 15 more 17 gives 7. And 5 power 16 more 17 gives 1. If you observe in this entire scenario, the results are uniformly distributed. So from 5 power 1 to 5 power 16 more 17, we got unique result. And that is why we said 5 is a primitive root of the prime number 17. If things are not clear, let's see this in a different way. Say, we are going to compute 5 power x more 17. We know 17 is a prime number and 5 is a primitive root. Then we will say 5 is a primitive root of the prime number 17. If 5 power 1 more 17 to 5 power 16 more 17 gives unique results. Say 5 power 1 more 17 gives 5. 5 power 2 gives 8. So when we carry out this operation, we get unique results. So from 5 power 1 to 5 power 16, we are getting the results that is actually uniformly distributed. So that is the important property of the prime number and the primitive root. So what we understand from this is that when we deal with 5 power x mod 17, and when we start giving the numbers for x, then we can see the result that is equally distributed. Say this x can be from 1 to any range, but still the prime number is 17. So this is applicable only when there is a prime number and we have a primitive root for that prime number. So we call this number 5 as a primitive root or generator. So it's clear that if we want to compute 5 power x mod 17, it is easy to do it. Say you are given with the number x and computing 5 power x mod 17 is easy. But think of the reverse situation. Say you are having 5 power x mod 17 and you are given with the result 12. Now finding what is this value of x is tough because x can be 9. 5 power 9 mod 17 will be 12. 5 power 25 mod 17 will be 12. 5 power 41 mod 17 will be 12. 5 power 57 mod 17 will be 12. 5 power 73 mod 17 will be 12. And there can be any value for this x. If x is given, computing 5 power x mod 17 is easy. But if 12 is given, then finding the value of x that resulted in this value 12 is difficult. So that is what I told you. It is easy in one direction, but it's hard in the reverse direction. So this is what the important property of a one-way function. I think now you can understand why it is called as a one-way function. Just correlate this with the coffee analogy which we dealt in the initial part of this lecture. So preparing coffee is easy, but reverting this is tough. So that's the important property of a one-way function. I think now you can understand this. So computing 5 power x mod 17, if the value of x is given, then it is easy in one direction. But think if 12 is given and if you are required to find what is the value of x, it is hard in the reverse direction. This is what a one-way function is. Let's see the theoretical aspects. So we are going to compute, for example, g power x mod p, where g is the primitive root of the prime number p and x can be any number, but computing g power x mod p is obviously easy in one direction. Let's take an example. Let's take 2 power x mod 7, which is equal to 4. Now, what value of x will give the result 4? If you take x is equal to 2, then 2 power 2 is 4. 4 mod 7 is 4. If you take 5, 2 power 5 is 32. 32 when it is divided by 7, we get 4 as the result. So there can be any number of values for x possible. If 4 is given, it's really tough to decide what is the value of this x. Can be 2 or 5 or anything. For smaller value of the prime number p, that is for smaller values of this prime number, it may be easy to find x. But think if the prime number is a large prime number or a very large prime number, then finding this x is hard. If the prime number p we take is large, then the time and effort to find this x is very hard. So that's the logic behind one-way function. So the strength of a one-way function is depending on how much time it takes to break it. If you take a large prime number p, even if you know what is the primitive root, it's really difficult to find what's the value of the x we used in order to get the result. So that's the property of a one-way function. The next lecture we will solve some examples, then you will understand things clearly. And that's it, guys. I hope now you understood the discrete logarithm problem, and we also have come to know about one-way function and its strength. I hope the session is informative, and thank you for watching. Prime number p, even if you know what is the primitive root, it's really difficult to find what's the value of x we used in order to get the result. So that's the you understood for watching. In the last presentation, we have understood what is discrete logarithm problem with an analogy. In this presentation, we will see a simple solved example in discrete logarithm problem. If you are directly watching this lecture, I request you to watch my previous lecture so that you will gain the knowledge about what is discrete logarithm problem and how hard it is to find. Let's step into the question. The question is, solve log to the base 2 9 mod 11. It's really simple to solve these kind of questions. Let's see the solution now. So here, what are the information that are given? Here, the prime number which is given, where p is equal to 11. So I'm mentioning this 11 as p, the prime number. And what is this? This is the base, right? So I'm making g to be 2. And what is this? This 9, I'm referring it as x. So from this, it's clear that the prime number p is equal to 11, g is equal to 2, and x is equal to 9. So these are the given data from the question. Let me now show the equation of solving this. So this is the general equation that I'm going to use in order to solve this kind of problem. So here, log to the base g, x is congruent to n mod p. Before proceeding with this problem further, just recollect what is the main idea of discrete logarithm problem. Finding the exponent, right? How hard it is to find the exponent is the real challenge. If you have a small prime number, obviously you can easily find the exponent. But if the prime number is of 100 digits or if the prime number is very large, then it is very difficult to find the exponent. Now how to solve these kind of problems? So as I already mentioned, this is the equation that we are going to adopt in order to solve this problem. So this is log to the base g, x is congruent to n mod p. Let's have this x here. So mathematically, if you want to retain x here, so obviously x is congruent to this log to the base g. This g goes here, right? This acts as a base, and this n takes the power position. So x is congruent to g power n mod p. And we know what all the given data in the question. P is equal to 11, G is equal to 2, and X is equal to 9. Just substitute all the values here. So X 9, G is 2, and we are required to find N, and we have P to be 11. So we get the equation as 9 is congruent to 2 power N mod 11. So we have substituted the values and we got this equation. Now we are going to find the exponent. What is the exponent? N is the exponent. So obviously we are now required to find the N. How to find this N? This congruent equation must be satisfied, right? So let's try N is equal to 1, 2, 3, up to some numbers so that this particular congruent equation is valid. Let's try 1. 2 power 1 is 2. 2 mod 11 is 2. So it's not 9. Then let's try 2. 2 power 2 is 4. This is 4 mod 11. 4 mod 11 is 4. So this this is an invalid congruence. Let's try 3. 2 power 3 is 8. 8 mod 11 is 8. 2 power 4 is 16. 16 mod 11, we get remainder 5, right? So 2 power 4 mod 11 is equal to 5. So this is also an invalid congruence. Let's try 5. 2 power 5 is 32. 32 mod 11, we get 10 as the remainder. So this is also an invalid congruence. Let's try n is equal to 6. So it becomes 2 power 6. 2 power 6 is 64. 64 mod 11, we get 9 as the remainder. So when n is equal to 6, we get 64 mod 11, and this equation becomes a valid equation. So when you try n is equal to 6, we get a valid equation, and the exponent that we have found out here is 6. So the answer to this question is 6. I mean, log base 2, 9 mod 11 is 6. Before we sign off, let's take become 4. 64 mod 11, we get 9 as the remainder. So when n is equal to 6, we get 64 mod 11, and this equation becomes a valid equation. So when you try n is equal to 6, we get a valid equation, and the exponent that we have found out here is 6. So the answer to this question is 6. I mean, log base 2, 9 mod 11 is 6. Before we sign off, let's see the homework question. The question is, find the value of x in 2 power x mod 7, which is equal to 4. So I have given a different equation here, and I want you to try the value of x from 1 so that this becomes a valid equation, and find the value of x and post your answer in the comment section. And that's it, guys. Today we have solved a simple example in discrete logarithm problem. I hope the session is informative, and thank you for watching.